Today we're going to be talking in depth about two projects that we worked on in the past year. And we'll try to give you some insight into the ideas and inspiration behind them, but also a lot about our working process and the technical details that sort of went into making them a reality. Nervous System, as you can tell, consists of myself and Jesse. And we started our studio in 2007 when we were both still in school. And we wanted to use Nervous System as a creative outlet for cross-disciplinary experiments that really didn't fit into the structure of our educations. Jesse has a background in math and computer science, and my background is in biology and architecture. Our projects focus on three main areas of research: science and nature. So we're interested in understanding the processes by which shapes and forms and patterns emerge. And this interest really embraces diverse phenomena, including biological, chemical, geological, and physical phenomena. And we're also completely fascinated by digital fabrication. We're interested in exploring what new opportunities computer-controlled manufacturing technologies make possible and how they can influence the way we construct the world around us and express ourselves. Combining both of these interests, we're interested in something we call co-creation, which is thinking about how we can create new types of design tools that are more powerful, accessible, and democratic. Our projects often start from a natural phenomena. Our hyphae project from 2010 was inspired by how veins form in leaves. We translated this natural inspiration into an algorithmic design system that we could use to explore this pattern space and develop new types of structures not seen in nature. Ultimately, we translated our 2D inspiration into a three-dimensional growth system that's sort of space-filling, and then that into a collection of 3D printed lamps, each one of which is one of a kind. So really interested in leveraging these subjects together to come up with ways to combine digital fabrication and algorithms to make truly one-of-a-kind products.
So we're really interested in how digital fabrication can open up new ways to make things. And it affords all these new opportunities where you can make things that are very complex and intricate just as easily as you can make a simple cube. Or you can make things that are all different just as easily as you can make mass-produced designs. There's no overhead of tooling or anything like that. And also, how this is really opening up manufacturing and making to more and more people. You don't need extensive experience in some specific manufacturing technique that only works in a certain way. These tools have become proliferated in the last few years, such that they're now in public libraries and schools and offices and people's homes. So this is all really exciting, except that a lot of this is much more dream than reality. And from our perspective, one of the key missing components is software. Design tools are expensive. They can take a lot of training to master. It's very difficult to do these sorts of things like making very complex or making variation. And so one of the things that we're interested in is using these techniques to sort of create new, playful design experiences where sort of anybody can go and design an object that is very complex, might be difficult to make using traditional modeling tools, but runs in the browser, uses new web technologies and simulation to make these new tools accessible.
So the first project we're going to talk about is one that we're currently working on called Floriform. Every talk at Eyeo has to have a quote, I decided, so this is our quote of the day. Organic form itself is found, mathematically speaking, to be a function of time. We might call the form of an organism an event in space-time and not merely a configuration in space. So as you can tell, this is where the title of our talk came from today, and it's a quote from Darcy Wentworth Thompson from the early 20th century. And what I love about this quote is the way that it sort of crystallizes the way in which forms we see in nature are the result of complex dynamic processes. These processes grow and adapt to different conditions, and the resultant shapes that we see are expressions of the processes and conditions that generated them. I see this idea of form as a process as a really interesting counterpoint to how humans have traditionally constructed objects. We take a very top-down approach to design. We create objects essentially by specifying direct, sort of precise measurements, shapes, curvatures, and often we determine the final shape of an object at the very beginning of a design process. Computers offer new ways of making, but most design software tries to mimic or reproduce methods by which we've made things before computers. We have software that gives the experience of drafting, sculpting, model building, and really specific stuff like shipbuilding. They translate how humans have traditionally worked with materials like paper and wood and clay and metal into some sort of strange digital analog of those experiences. Our work attempts to propose a sort of different direction. We're taking inspiration from nature's process-based designs, and we focus on developing interactive processes that we can engage with. So instead of creating static designs, we create dynamic systems, and instead of drawing structures, we're interested in growing them. This project, then, is somewhat esoteric, but the topic is differential growth and the development of form in biological processes. If you start with a sort of very simple idea, how does an organism go from a single cell to a complex differentiated structure? If you start with that single cell and you're just to divide and grow evenly everywhere, what you'd end up with is essentially just a formless blob. However, through carefully coordinated subdivision and differentiation, biological systems are able to produce structures with incredibly specific reproducible forms and functions. The idea is actually really simple. Like if you have something and some of it's growing faster than other parts of it, you're going to end up with this differentiated shape. And we can call that differential growth. And if we have this differential growth at a very microscopic level, you start to wonder, how does that lead to complex macroscopic shapes? And how do the macroscopic shapes then influence the underlying cellular growth processes? And what's the interplay between all those processes that are happening at a tiny level and the nature of the materials themselves, their physical properties? And that's sort of what we want to explore in this project. So we're talking about this differentiation and inhomogeneous growth, and how does that inhomogeneity occur? It turns out that the body plan and almost all the structures of an organism are imprinted very early on in its development. It starts with a simple gradient in an embryo, which can function essentially as a map for the position of every cell in its body. In a fly, for instance, which is what you're seeing on the screen, a gradient of a single morphogen can define the anterior-posterior axis of its body. So essentially, where's the head and where's the butt? A gradient of a simple morphogen can define that. And then trigger a cascade of other genetic pathways that in turn produce more morphogens and create secondary gradients that define its segmented body plan, which is what you're seeing on the screen. Organisms are also affected by environmental gradients. For instance, in plants, there's a series of very well-documented behaviors called tropisms. Tropisms are directional growth responses to directional stimuli. They serve to aim growth towards resources or away from hostile environments. Plants are affected by gradients of light and temperature, humidity, oxygen, nutrient availability. It can also respond to gravity and touch. These plant movements, if we simplify it a lot, are essentially just really well understood examples of differential growth. Plants can grow towards the sun by an asymmetrical elongation of cells on either side of a plant organ. So for instance, if we're thinking about these really simple diagrams we drew, we have the cells indicated in red. Those are growing faster than the cells that are more white, and that leads to a bend, produces curvature. If we were to think about that in terms of surfaces, you could imagine having essentially just two layers of cells. If the bottom layer is growing more quickly than the top layer, that produces this concave shape.
So the origin of this project was when we came across some research by a professor named Mahadevan, who's at Harvard. And we were looking into the form of leaves, and he had kind of a different take on how shape could be generated through differential growth. So rather than this kind of sided growth, he proposed that the shape of certain types of leaves and blooming flowers could be explained by differential growth towards their edge, so growing faster towards the edge than in the middle. And this could explain how sort of a curled up initial petal could unfurl and then curl along its edge. We're really interested in this idea because unlike this kind of sided growth where you have a one-to-one relationship between growth rate and curvature, this has a much more emergent form that you don't necessarily anticipate just from the simple rule of grow more towards the edge. And the resulting form is very complex and would be extremely difficult to describe and explain by specifying each curvature in each location. So after we came across this research, we started to notice all sorts of these kind of undulating forms that could be explained by this idea of differential growth towards the edge. And not just in plants, but in all sorts of organisms. So you have the arms of jellyfish, anemones, certain types of fungus, mutant cactuses, bryozoans, corals.
This one is a bit of a side, but one of the ones that we showed on the previous slides is the back of a lettuce sea slug that I photographed while scuba diving. And these guys are really cool because they use the increased surface area on their back to store chloroplasts that they steal from algae. So they have a practice called kleptoplasty, where they eat algae, they harvest their chloroplasts, and then they array them in this back ruffle and have sort of like a mobile solar photosynthetic farm, which is cool.
This is another one of our favorite examples. So this is a flower called a coxcomb, and on the left is sort of its normal growth. It grows these kind of branching flowers that form a cone, but it can have a mutation called fasciation, where normally a plant grows from what's called an apical meristem, which is sort of the growing part, and that growing part will split and form branches. But here, instead of forming branches, it just starts to elongate and form a line. And when that happens, this flower creates this amazing ruffled shape that's sort of unlike any other flower I've ever seen. And so we started to want to explore this space of differential growth, and how could one type of differential growth form these branching structures and then switch to this formation of these undulating surfaces. And so when you build a model of something, the idea is to kind of simplify it to the most bare bones description that still has the behavior that you're interested in. So plants are extremely complex, and they're made of cells. Each of these cells have pressure inside of them called turgor pressure. They differentiate into complex structures like veins. They have all sorts of chemical processes going on. But we throw all of that out, and we just sort of try to describe the simplest kind of material, which is something with linear elasticity, which basically just means you stretch it a certain amount and it pushes back in a proportional force. And then we can simplify this model even further. We're sort of only interested in these lamina-like structures, which can be described as thin shells. So they're much thinner in one direction than another. And so instead of describing an actual three-dimensional material, we can describe a 2D surface embedded in three-dimensional space. And then in order to do computation on this surface, we break it down into triangles, and we model its elasticity by having a spring-like force on every single edge of our triangle, and then a bending force that resists bending in between the faces of each triangle.
So we built this system based on the model that Jesse described. And the first thing we wanted to do was explore sort of different types of idealized growth scenarios that we see in plants. Like we were just talking about, how do different distributions of morphogen or growth potential produce different shapes?
So this is kind of like the base condition. This is uniform growth, growing the same everywhere. And unlike what you might just think normally, this doesn't mean that it just scales up, but it actually forms this kind of wrinkled, weird form. So that's sort of our base condition.
The next one we have is the same surface we had before, a hemisphere, except for growing the same everywhere. Now it's actually growing from a single growth point that then splits, and those splits produce branches. So this is inspired by the idea of an apical meristem in plants. This one is the same sphere with the same growth point, except for instead of allowing that point to split, it just continues to expand, producing this crested growth. So this one was somewhat inspired by the mutant flower cactus phenomena. And the last one is the edge-based growth. So we're growing faster at the edge of the surface than we are towards the interior, and that leads to this convoluted folded shape, which was our initial inspiration for the project. So now that we've built some computational system, we've established sort of these baseline of growth modes, the question becomes, like, where do you go from here? Like, how do you explore this further? And this image for me is standing in for somewhat our philosophy for how we work with dynamic systems. So I would describe our practice as a little bit like digital gardening, except for instead of cultivating plants, we're trying to cultivate algorithms. And ultimately, we want to create or breed systems that have their own innate behaviors, but that we can also sort of sculpt and manipulate. And as we're developing our software, we encode sets of influencers, gradients, and manipulators that enable us to interact with and sculpt the system. There's also a kind of interesting interplay between what the system does innately and our sort of manipulations of that. There's like a back and forth as we continue to like go and restructure how it works and completely change all of the code, and then what it does itself. So the next things we're going to show you are sort of a set of these controls that we're building into our system to explore and guide it.
So here we're changing the material properties of the surface. We're varying the resistance to bending from left to right. So if it has a very small resistance to bending, the wavelengths are much smaller, and a large resistance to bending, you have much larger undulations. Here we're introducing an external force like gravity, except in this diagram, gravity is going up in the lower right and into your face in the middle. And this allows us to kind of elongate and shape the growth a little bit. Here we're sort of looking at different ways of distributing the growth rate through space. So on the left, the rate of growth falls off very quickly as you move away from the edge. On the right, it falls away very slowly. And you get these sort of very different characters of the way that it emerges.
In all of these videos, the color that you're seeing on the surface is an expression of the growth rate. So the more turquoise something is, the faster it's growing, and the more white it is, the slower it's growing.
Here we're introducing anisotropic growth. So instead of everything growing the same amount in all directions, we grow more in one direction than another. So on the left, we're only growing perpendicular to the edge, and no sort of ruffled shapes emerge. And on the right, we're growing purely parallel, and in the middle, it's isotropic. And this is actually similar to what happens in a lot of real plants, where cells only elongate in one direction.
I don't know if we can start this over. Okay, so this one, as you can see, the surfaces are growing from distinct zones along the edge rather than the entire edge. And when I started making this example, I was thinking that I'd grow something like petals, but actually what we get are these sort of strange different degrees of symmetry that emerge, where the 5-degree symmetry one, which is on the right, the wavelength that the surface wants to make as it bends perfectly fits into what I'm trying to get it to do by growing, but on the other two, it can't quite fit, and it causes these weird perturbations and asymmetries, which I found interesting.
Oops.
Now I got us stuck on this page. There we go.
Here we're experimenting with changing scale or thickness of the surface through time. So as we're going, the thickness or scale decreases, and we get this kind of fractal effect of waves upon waves upon waves.
This one is more of an environmental factor, you could say. So it's just changing the growth potential through space. So not along the surface, but within the environment that the object is growing in. So you could think of this maybe as light or as nutrients.
Okay, so now we're going to go a little bit more into depth about how this system works and what we actually code into it. So we start out, we just bring in something that we've pre-designed, and usually that's a simple surface, like a lot of the examples we're showing are hemispheres. And then we have this loop as we grow the structure, and we have to do sort of these steps for each step of growth. So we're running a physics simulation that determines how our points move. We have collision detection to make sure things don't self-intersect. And we have to compute geodesic distance along this edge. So we're using the geodesic distance to control the growth rate. And so we have to compute distances not through normal space, but along the surface. And we're using kind of an interesting method to do that was developed in 2013. So a lot of traditional methods for doing this use some sort of modified Dijkstra's algorithm where you're doing like a shortest path calculation, and you're sort of directly measuring distance along the surface. But this takes a very different approach, where instead of doing that, it's using the gradient of heat or diffusion from the growing zones. And that's the same direction as the gradient of distance. And so we compute this gradient and then integrate it to get our distance. And a lot of these methods are taken from a group of computer graphics researchers that are called discrete differential geometry. Our physics simulation sort of is a fairly traditional physics model where we have a bunch of forces that we compute on all of our edges. We have contact forces from collisions. We have external forces like gravity. We sum all those up, and we integrate it with an overdamped implicit Euler solver, which I will not go into exactly what all of those words mean.
But then we get the positions of the vertices, and we move them. Yay. Okay. We also have collision detection because we don't want our surface to move through itself. That wouldn't be very realistic or useful. And we're using a somewhat naive collision detection system that's based on particles. So we're essentially building an ellipsoid around every vertex of our mesh, and then we're watching for if those ellipsoids ever intersect each other, and if they do, we create a spring-like force to push them apart.
And the reason it's an ellipsoid is so that it has a constant distance normal to the surface, so that we can control how close these surfaces get to each other, and it's proportional to this kind of the underlying triangulation tangential to the surface, so that things can't slip past each other. And this is kind of a video of showing all of these components in action. We have the growing surface, the underlying triangulation. It constantly has to re-subdivide as it grows and becomes more detailed. The color indicates the growth, and then here are the collision bodies doing their job. It's not self-intersecting.
So we've begun sort of translating some of these digital experiments into physical sculptures using 3D printing. We're also trying to kind of combine some of our algorithmic systems together. So the bottom one is kind of a hyphae venation network grown on top of a fluoriform structure, which is interesting. We're also using color 3D printing to kind of produce objects that express their growth rates on the surface. So yellow is growing more and purple is growing less. And then last year built some devices inspired by 19th century zoetropes to make essentially animated sculptures that look like they're growing. And then I guess one thing that we haven't mentioned yet is that at Nervous System, we often try to take all of these esoteric ideas that we're dealing with and then disseminate them into the general public through affordable objects. So we're using our fluoriform system to grow a jewelry collection. We develop a specific growth process for a specific surface, produce a specific piece of jewelry, and these are then 3D printed. So that was a ring, a cuff, a necklace, and a cuff. And then we feel pretty strongly that ideas like these shouldn't be limited to academia or research or purely theoretical projects, but should diffuse into our daily lives, and that even products can embody really complex ideas.
So now we're going to switch gears to a completely different project that has a focus not on natural processes at all, but looks more at digital fabrication and co-creation. So this project started in a really strange way for us. We don't normally do a lot of contract work, but in the summer of 2013, we were approached by Google's ATAP group, Advanced Technology and Projects. They're the same people who are working on Project Ara, the modular cell phone. And so in addition to doing that, they also had this project where they had a van that was full of 3D printers, both desktop ones and industrial machines. And they wanted to drive this van across the country, take it to events and universities. And what they wanted us to do is develop design experiences where somebody could come up to this van, design something, and make it all in under an hour as an accessory for their phone or whatever. That was the justification. And so this idea is kind of crazy. They're like, let's put hundreds of thousands of dollars of equipment in this van and just drive it around. It's going to be awesome. But it sort of gave us this opportunity to explore customization in a new way, because we were used to doing things online, just putting something up, but we didn't ever do anything with people face to face. So this was a way that we could explore this. But the problem is that 3D printing is really slow. So this little GIF shows this object emerging before your eyes, but actually that print takes 8 to 12 hours. So printing something in under an hour, and actually designing and printing in under an hour, is pretty challenging. And you essentially have to print something that is almost flat, which is kind of paradoxical. You're using a 3D printer to make something that's not very three-dimensional. And so we had this idea where we could use the ability to make complex interlocking objects to print something that would be very flat, only 3 millimeters tall, but that could transform into a more interesting three-dimensional shape. It could be something like a bracelet, and then rather than kind of like a traditional watch band type of mechanism, it would be more of a surface of triangulated structures. So we began to prototype these on our MakerBots. All of these were printed just on a simple desktop machine, all in one piece. There's no assembly. And then ultimately what we created is this bracelet where each module can be customized, and you can tweak the shape and the color. And there's an NFC tag embedded in it so it can talk to your phone. We took this around to maker fairs, and people would walk up and make their bracelet, and they'd get it. And that was fun, that was cool. But then we sort of we had this weird project that we'd done on a van.
Yeah, so at the end of the project, we're left with these kind of like really fascinating artifacts that hinted at something maybe approaching fabrics, but made with 3D printing. And the more that I thought about it, it didn't really seem that weird to make fabrics with 3D printing. After all, textiles are purely human constructions. They're raw materials that have been transformed to have completely different properties and behaviors based on how they're arranged through space. That arrangement seems to matter more to how a fabric behaves than the raw material itself. So whether it's woven or knit might matter more than whether it's cotton or wool. So essentially, you could think of textiles as constructed materials. And then additionally, we might think of them as historically computationally mediated materials. The jacquard loom, which was first demonstrated in the 1800s, used punch cards to include weaving instructions to produce richly illustrated textiles. And perhaps we could view this weaving machine as the first computer, or at least an important predecessor to it. You could see textiles not only as constructed materials then, but computationally mediated materials. 3D printing then could be really fascinating for a way to make new computationally constructed materials like textiles, because it allows us to make increasingly complex computed configurations of matter, of stuff, that could result in kind of metamaterials whose behaviors can vary through space. So our hinged sort of tessellated constructions, we found that they were like a really interesting hybrid between hard and soft materials. They're not quite one or the other. And we had made some pieces like the piece you see on the screen. It's a necklace that's wiggling around. And these were very small, though. They were about the size of the 3D printer that we were using. And we started to think about, could we expand past the confines of our tiny 3D printer and make something a little bit bigger? Like I got into my head that I wanted to make it dress. And I was like, how would this hard, soft stuff move if I was walking around with it? How would it flow? But I had to make it first. And our printer was small. So a lot of projects in the realm of digital fabrication, they want to make a big thing, they design a big thing in computer, and then they chop it up into a lot of itty-bitty parts, and then they fabricate all those individually, and then they assemble them. So you end up with, let's say, thousands of unique components that you have to manually organize and assemble. And this can end up being considerably more work than the entire design process that you went through to generate that object. So you've essentially just kind of taken computation and made your life a lot harder. We had kind of an inkling that we could do something a little bit different, though. So maybe we could take advantage of the fact that the thing we're making is flexible and use that flexibility to bend and fold it into a smaller configuration that we could print in one piece. So what if we can fold the thing up and then print it like this and then unfold it from the machine into a finished component? That seems like a really awesome idea. So we thought we'd work on that. And as we started thinking about that, we started thinking about making clothing in general and how this could really kind of, for us, change the way you think about making clothes entirely. Bodies are three-dimensional, but clothing is typically made from flat material and flat patterns, and all of the process happens in 2D, and then it's painfully reconstructed into a 3D object. But if we could print something like this all folded up in one piece, then we could start with just a 3D scan of your body, and then produce a fully custom fit garment where nothing ever has to be cut, sewn, or assembled.
So we had this idea, but there are actually a lot of things that had to go into taking this idea and making it a reality. And there are lots of different facets to this project. So there's issues of just manufacturing and 3D printing, and we have to deal with materials and tolerances and different machines. How do we actually go about designing these garments? So, how do we make a tool that would allow anybody to customize their own thing? Dealing with bodies and fit and how we actually design on a 3D scan was very tricky. And then finally, sort of the heart of the project being the simulation and folding it for manufacturing. So when we were doing this Make with Moto project, we were printing these on desktop machines using FDM printers, which is sort of what people have become familiar with in 3D printing. But once we were done with that, we could move to sort of larger, more industrial machines that work on a different principle. So we're using selective laser sintering, which prints materials from a powder. So you start out with a powder, it lays down a layer everywhere, and then melts together the solid areas with a laser, lays down another layer. And what this means is you ultimately end up with your object packed in a giant cube of powder, and then all of the excess powder sort of falls away afterwards. And this allows you to make much more complex, intricate, interlocked components than you can on a desktop machine where things need to be supported in space. And this project really hinges on hinges. And so when designing our hinge, we have to sort of work with the limitations of the printer and the material that it prints, nylon. And one of the issues is that the strength and tolerances and errors and all this depends on the orientation inside of the machine that it's being printed. But because we're printing it crumpled up, we don't actually know what orientation anything is going to be printed in. So we sort of have to design and prototype knowing that anything that we make maybe won't work when we print it the next time. And so we ended up making dozens of different hinge designs and prototyping all of them physically and testing them. And we sort of want to make them as small as possible because that is the limitation of how kind of intricate we can make the structure and how fluidly it can flow and move. And the problem is that then we end up working at sort of the very edge of the tolerance of the machine. And so if we make it too tight, it will fuse together and it won't move at all. If we make it too loose, it'll fall apart or it won't really have the behavior that we're interested in. So prototyping these became very kind of difficult. So we started out small. This is the first object we ever printed crumpled up. It's sort of a necklace. That worked. So we scaled up and we made this belt that Jessica's been fondling during the talk. And this was the first thing that we'd ever made from a 3D scan. And that worked, so we scaled up again. This was sort of our first test at scale. This has over 1,000 unique components that were all printed in one place, made from the same 3D scans, sort of testing more how it would behave and move and fit.
So all of the things that Jesse just showed you, all of those prototypes were essentially made in computer programs that didn't have any user interface whatsoever. So it's very difficult for us to specify the shape and pattern of the garments. But our ultimate goal was that we wanted to make some way for anybody to design their own garments, like harvest the power of digital fabrication to open up possibilities. So we set our task of designing maybe the world's first web application for making 3D printed clothing or something like that, which we called Kinematics Cloth. So this is a JavaScript and WebGL app that runs in your browser completely in real time. And the idea was essentially just to set it up so you could design a simple garment. So you can design dresses and shirts and skirts. There's what we hope is an intuitive interface that's sort of like painting and sculpting. So you can sculpt the sort of shape of the skirt and the hemline. You can paint on these different densities of triangles, which define the 3D printed structure itself, and then apply these module styles, which define sort of the porosity and pattern of the garment. And then ultimately you can save and share and edit your design later and things like that. And of course, they can be printed. The heart of the system is kind of this live remeshing algorithm that we developed that's happening constantly as you're painting the garment. So we're essentially trying to match the tessellation of the garment to the user's input as they're live painting on the surface. Painting on these colors defines different densities of triangles, and we sort of meet those densities with an iterative remeshing algorithm that's constantly updating. We split edges and collapse them and flip them. We also have to smooth the shape of all the triangles to maintain good triangle shape, so the hinges can be fit in properly. And we also have to constantly be projecting all the vertices onto the body to maintain fit. These are some of the module styles that I was talking about. Currently, we just have these 4, and they're just sort of intended almost to be diagrammatic. You could have a solid dress, a perforated dress, one with crazy protrusions coming out of it, or really something anywhere in between, any of those things.
And then there's this sort of separate issue of bodies, and how do we design something on somebody's exact body shape, not just a generic size or generic measurements. And we thought there's this proliferation of different 3D scanning technology and depth cameras with Kinects and Intel RealSense, and they're going to be on laptops and phones and all of these things. So we have these ways to capture people's body shapes. But the problem is that 3D scanning can be very glitchy and noisy and unpredictable. They have all these errors where places that are in shadow will have holes in them, or you can have weird duplicate surfaces. And then even if we could have a perfect, clean scan, we have all these other issues. So we need semantic information of where's your torso, where's your neck, where do the sort of elements of the dress go? And then even if we know those things, somebody can be scanned in an arbitrary pose. And if you're posed like this, holding your hands on your hips, and your hands have kind of like merged with your stomach, we can't really design a dress on top of that. So while we were working on this, we happened to luckily meet some people who were working on this exact problem. Their name's Body Labs. They're a startup in New York. And they built a parametric body model that's made from machine learning of thousands of scans of different people. And so what they do is they can take 3D scan data or measurements and build this consistent model that's clean. It can be moved into different poses, however you want. And additionally, sort of any one point on one body will map to the same sort of general part of somebody else's body. So a point on the stomach will always be in that area on the stomach. And so what that allows us to do is we can have somebody design something for them and share it with other people, and then anybody can have that same design and map it onto their body shape.
So the cornerstone of this project, though, is simulation. So at the beginning, we're like, oh, let's just fold it up and shove it in the printer. And then we got to the point where we actually had to do that. And the question is, how do we do that? And how do we make sure it's accurate? Can we actually even do what we claimed and reduce the size of the garment for 3D printing? To simulate our kinematic structure, we used a rigid body physics solver. We experimented with a lot of different libraries while developing this system. And the problem apparently is that no one else is trying to develop 3D printable objects that need to be folded. So there isn't really a tool that's built with our needs in mind. There's often a tension in our work between developing our own tools, which can be very time-consuming, and using something that somebody else has already made, which may not be suited to the job. In this case, we thought we could probably use something that somebody had made already. Right now, we're using the physics solver by NVIDIA.
So when we're simulating this, we're not simulating the actual exact geometry that we're printing, but we're simulating a simplified, idealized shape, because otherwise it's way too computationally intensive. So we start with this design triangulation. We build these idealized bodies with idealized hinge constraints around them. And we have this kind of issue where our actual shape is not an idealized hinge. It actually has a fair amount of play, and that allows it to move and flow more fluidly and allows us to fold it in real life much more compactly. So we actually kind of want to introduce an amount of error into our simulation to kind of get that fluidity back. But our tolerances are extremely tight. So we sort of have this tension of if you introduce too much error, you get something that's unprintable, unusable, and if it's not enough error, it's very stiff, it won't fold very well. And so after we fold it, we have some error, and we have to do this refitting procedure to sort of map it back to a perfect printable shape.
One of the neat things about having this robust simulation for folding the garments up is we can also use it in the design process. So we can take that simulation and as we're designing garments, look at exactly how they're going to drape and how they'll move to have that sort of play back and forth. While we initially just conceived of crumpling up the garment in a ball like you're throwing in your hamper, later we figured out that it'd be actually much more efficient just to fold it like you're putting it in your dresser. So we compress objects through a series of collisions with surfaces. And this right now is showing you the folding process we used for our first dress. So the overall bounding box is reduced by over 85% by folding.
So the first dress we ever printed was actually for the Museum of Modern Art. And we had met Paula Antonelli, the design curator at the MoMA, and she had seen this sort of concept video that we'd made, and she thought like, oh wow, this is really amazing. I would love to, acquire one. But I don't know if she realized at the time that we'd never actually made one. And we went to the Shapeways factory. This is the printing of the first dress. It's printed in New York. And a couple of weeks before this, we had done tests to make sure that the whole folding system and our hinges that we had made would work, because we had been changing things. And we printed a skirt that was completely fused together and didn't work at all. And we didn't really have any time to go through another round of prototyping and make sure that it would work. So when this came out, we didn't have any idea if this was going to succeed. We didn't know if we were going to have this lump of plastic that was completely useless or a beautiful dress that we had to take to the MoMA the very next day for a meeting. But luckily, we took it out, we unfolded it, got some of the powder out, we called our friend, and we were like, the dress printed, you got to come down to the factory and try it on.
This was a moment of incredible stress and then incredible relief. It was amazing. So happy. So one of the things that we thought about when we were working on this dress is making something that was actually wearable. There have been a lot of sort of news stories about 3D printed garments, which look absolutely fantastic and crazy and futuristic, but you can't actually sit down in them and you can't move in them. It's more like wearing a sculpture. They look amazing, but they don't at all conform and move with your body. So we took a lot of care when we were thinking about how to develop this whole system to focus on the wearability aspects. And one thing that ended up being really exciting, which may be a little bit boring to everybody else, but I was really psyched to see how well the simulated draping that we'd used to design the dress matched the real draping that we had once it was being worn. And then when you twirl, you can sort of see the undraped form, which is super cool. And then here we have the first dress that we made, and it's a custom fit dress. It's composed of over 2,200 unique triangular panels that are interconnected by over 3,300 hinges, and all of these were 3D printed as a single piece in nylon. While each component is rigid in aggregate, they behave as a continuous fabric, allowing for the dress to flexibly conform and fluidly flow, sort of with body movement. And unlike a traditional textile, this dress is not uniform. It varies in drape, rigidity, flex, and pattern throughout space, and the entire piece is 100% customizable from fit and style to flexibility and pattern. For us, this is just a baby step in a larger project about thinking how can we leverage digital fabrication and co-creation to create complex digital materials and products. So really, how can we empower the design process through all of the technological tools that we have at our disposal today? Right. So this is who we are. We're Nervous System, and send us your questions by email, I guess, since I think we're out of time.
We can do.
I'm going to be really embarrassed if I missed this, but I have to get it off my chest, so to speak. You print this dress all in one piece, fold it up. How do you get it on?
It opens up on the side, so the design you can sort of see here, they're like these buttons which are generated. So in the app, the whole left surface gets cut automatically and double triangles are produced that snap into each other, sort of like plastic jacket snaps that go all the way down the side.
Wow. That's amazing. Thank you so much.
Spend a lot of time doing really boring stuff like designing and testing snaps for 3D printing.
The thing that I just want to do is seeing all of the the first part of your talk and then even this, I just want to play with it. I want to try it. Where are there tools to play with some of that growing things you were doing? It sounds like there's an app to play with the textiles. Like, where can we get our hands on tinkering?
Well, a lot of times we kind of suck at releasing things. So a lot of the sort of more deep nature-y things are very slow and difficult to use, and like we were sort of describing with the kinematic software, they exist in this pre-state where there's like no user interface whatsoever. So we'd like to make more things available that people can play with, and we sort of started to do some of that, but it ends up being very computationally intensive and difficult to make something slow into something that would be interesting for people to play with.
It doesn't run in real time at all. We typically limit ourselves to releasing things that run really interactively.
Thanks, guys.